If you think insulin is only about diabetes, think again. It affects your heart, your brain, your metabolism, and even your sexual health. Most people think insulin resistance and type 2 diabetes are the same thing, but they're not. You can have completely normal blood glucose levels and be highly insulin resistant. In fact, up to 1 in 2 Americans may have some degree of insulin resistance. Most people know having chronically high blood sugar levels is bad, aka diabetes. But did you know that having chronically high insulin levels is just as bad? There are many steps between going from being insulin sensitive to insulin resistant to eventually developing diabetes. Today, we are going to cover what insulin is, what it does, how things go wrong, how you can know if you are insulin resistant, and what you can do about it. I am going to get a little technical here, but knowledge is power. The more that you can understand and conceptualize what is going on in your body, the more control you'll have over how you want to deal with it. So stick with me. Insulin is a hormone with one primary job: get the right nutrients to the right cells after a meal to clear that nutrients from the bloodstream. When you have a meal, it's akin to you walking into your house with 15 bags of groceries and dumping them in the entryway. Someone's got to put those groceries away in the right location so that your entryway is free. That's what insulin does. Insulin will put glucose into your liver and your muscles primarily, and then it'll tell them to form glycogen from glucose. What is glycogen? It's just glucose molecules stuck together. Why does your body do this? Well, let me ask you a question. Would you store your eggs in the fridge one by one as opposed to using the carton? No, of course not. Your eggs would roll around in the fridge, it'd be a hot mess. The same idea in your body. Your body likes to store glucose in the form of glycogen where it's nicely packed together. It'll also tell your fat cells to stop burning fat and releasing it into the bloodstream because there is an influx of glucose in your body. It's like coming home and you're trying to put your groceries away, but your kids are in the way trying to take things out of the fridge. What are you going to do? You're going to tell them to go away until you're done. That's what insulin is doing by telling your fat cells to stop burning fat. And lastly, if your liver cells and muscle cells are full, they can no longer pack away any more glycogen. Insulin will tell your liver to turn the excess glucose that it has into fat. And then that fat is packaged away and stored by your fat cells. This is like when your fridge and your pantry and your kitchen are full, but you still have some extra stuff. What do? You bring it down to your basement or you bring it to the fridge in your garage. So how does this actually all happen in the body? I'm so glad you asked. I'm going to give you a crash course in cell biology 101. If you can wrap your head around this concept I'm going to describe, you have a very solid foundation of understanding how your body responds to any type of change it encounters. Insulin is floating around in your blood and it comes across its receptor like a key into a keyhole. That receptor changes shape and thereby becomes a key itself for a piece of machinery in the cell. It unlocks that piece of the machinery, which itself then becomes another key for another piece of cell machinery, and so on and so forth until the last piece of cell machinery is turned on and performs the intended action. Like, take this glucose and stick it with this glucose, and then stick it with this glucose to make glycogen. This is called a signaling cascade because the signal, insulin, cascades from one guy to the other until an intended action has been completed. Okay, signal cascades are so cool. It's not that one signal produces one action. What actually happens is one signal can branch out like the roots of a tree to have multiple actions that synergize. For instance, insulin, one signal. can turn on the cell machinery to turn glucose into glycogen, but also through another path, the machinery to turn glucose into fat. The last point here is the cell machinery that insulin turns on is dependent on the cell that it is attached to. For example, both liver cells and muscle cells, insulin can activate the cell machinery that turns glucose into glycogen. But because these different cell types also have unique cell machinery, insulin can have unique impact. In the liver, as we discussed, it can activate cell machinery to make glucose into fat, but it can't do that in muscle because that machinery doesn't exist in muscle. Conversely, in muscle, it activates the pathway that allows for glucose to get into the cell, which is not the way that glucose gets into the liver. But notice here, and this will become important later, so really focus here if you haven't focused yet. If I knock out the ability of one of these to pass on its message to the next one, I can effectively turn off part or all of the action of insulin, depending on how early in the cascade I knock out that signal. This will be important later. But first, let's put it all together and see how insulin works. Okay, so when you eat a meal with carbohydrates or glucose in it, the glucose is absorbed through your small intestine into your bloodstream. It goes to your pancreas, where your beta cells of your pancreas sense the increase in glucose and release insulin. This, by the way, is a signaling cascade. The signal is glucose. There is a cascade that happens in the cell, and the last action is that insulin is released. All right, insulin is flowing through your bloodstream. The first organ it encounters is the liver. It binds the receptors on the liver cells. It cascades its message. And as we know, it tells the liver, take the glucose and make it into glycogen. Stop making glucose from other things like amino acids, which is the byproduct of breaking down proteins. Yes, your liver can make glucose from other things. And especially if there's an excess of glucose, it tells your liver to convert glucose into fat in the form of triglycerides, which are packaged out to be stored in fat cells. Okay, then it keeps going in the bloodstream and it's hitting your muscle, binds the receptor, the cascade begins. Probably insulin's most famous role is to take the GLUT4 transporter from inside the cell up to the cell surface. You can think of it as like a straw that it sticks into the cell surface that now allows sugar, glucose, to come in. Through another branch of the signaling, insulin tells the muscles to change glucose into glycogen. And through yet another branch, it also tells your muscle cells to not break down protein. Okay, so then it's done its job with its muscle cells. It is then going to your fat cells. It binds its receptor, signal cascade, and it's telling the machinery to store fat in the form of triglycerides. It also blocks the cell machinery that takes triglycerides and breaks them down into fatty acids. Now, if you've ever wondered what is the difference between triglycerides and fatty acids, triglycerides are 3 fatty acids stuck together by a carbon backbone. Why does your body do this? It goes back to that same analogy with the eggs. Just like your body likes to store glucose in a nice, tight, neat package called glycogen, it likes to store fat in a nice, neat package called triglycerides. If fatty acids were left free, it'd be the same thing as eggs rolling around in your fridge. It's not a good thing. And lastly, in your blood vessels themselves, it triggers a signaling cascade to produce nitric oxide, which is important for vasodilation or dilating your blood vessels. What that helps do is to get nutrients faster to your muscles and your fat cells so it can clear it out of the bloodstream. All of this is designed to feed your cells while keeping blood glucose levels normal. Now, you might be wondering, why is it so important that our blood sugar doesn't get too high? Well, it turns out glucose is chemically sticky, like sticky fingers. When it is chronically high in the bloodstream, it starts chemically reacting with fat, with protein, with DNA. And when it does that, it forms something called advanced glycogen end product. These molecules just gunk everything up and start to cause tissue damage, especially in your blood vessels, your kidneys, your eyes, and your brain. And they are believed to be the reason why you have such a high increase in the risk of cardiovascular disease, kidney disease, neurodegenerative diseases, such as Alzheimer's and other things too. It's like, when you find a half-eaten lollipop in your cushions and like everything is stuck to it, hair just like everything, and your cushions are sticky and ruined. That's because of the sugar on the lollipop. And the same thing is happening in your body. But you don't go straight from being healthy to having these advanced glycation end products. First, you develop insulin resistance. Okay, how does this happen? The first domino in developing insulin resistance is the overfilling of fat cells. At first, excess calories, fat, glucose, are safely stored in your fat cells or your adipose tissue. Those are the same thing. But each person has a genetic ceiling on how many fat cells they can make. Once you've reached that ceiling, fat cells don't multiply, they just grow in size. This is called fat hypertrophy, not to be confused with muscle hypertrophy, a different thing. So for example, Asians genetically have a way lower ceiling on the number of fat cells they can make, which means that their fat cells start to get fatter, bigger, way earlier than someone who is, for instance, Caucasian or white. Okay, the next step. As the fat cell grows and grows, areas of the fat cell no longer get oxygen to diffuse to those areas. It's gotten too big. This lack of oxygen is a signal to the cell. The cell activates a cascade due to the lack of oxygen where it releases factors called cytokines. It's like the fat cell is sending out an SOS signal, I need help, and calling part of your immune system to it. And the immune system itself is releasing cytokines to try to help what's going on here. Those cytokines that are being released interfere in insulin's signaling cascade. It's like another tree took up shop really close to insulin's roots, and now that signaling cascade from the cytokines is choking out insulin and disrupting its signal. So even though insulin is binding its receptor, the signal is not getting through and the actions are no longer being performed. So the fat cell refuses to store more fat. And in fact, insulin signal that tells it to stop breaking down triglycerides into fatty acids, it's deaf to, it's no longer getting that signal. So it keeps that process on, and now fatty acids are spilling into your bloodstream. Okay, this is where things really go downhill. The fatty acids, which are released by your overstuffed fat cells, travel throughout your bloodstream to your muscle and to your liver. They are hooligans. They are going to interrupt a lot of stuff. In the muscle, they get in the way of insulin's cascade. Remember that key going into the keyhole, they're getting in the way, so that isn't forming within the cell machinery. And therefore, that straw that was being brought up to the cell surface to let glucose in is no longer happening. And this is your first instance of insulin resistance. Insulin is there. It is trying to activate the signal to make your muscle bring in glucose, but the signal is being interrupted by the fatty acids. This is an enormous problem because your muscles are your biggest disposal of glucose. Shutting all of those muscle doors effectively is just going to spike up your blood glucose. Now, in the liver, remember I said there's one branch for making glucose into glycogen. There's another branch for making glucose into fat. The fatty acids are not interrupting this pathway of making glucose into fat. So insulin is sitting on the liver receptor and still telling it to make glucose into fat. And what ends up happening is, because of this constant signal from insulin, your liver keeps getting the signal to store more and more fat. And that is how fatty liver disease starts to progress. And on top of that, it starts to spill out triglycerides into your bloodstream, which is why now you start to have an increase in triglycerides in your blood. At this point, blood sugar levels are still normal, but insulin levels are now elevated because your pancreas is working harder to produce insulin to counteract the resistance. Chronically high insulin leads cells to downregulate the insulin receptor. So high insulin makes there be less receptors on cells, so you need even more insulin to get the same action, and it becomes a escalating, accelerating problem. Okay, so even before blood sugar levels start to rise, before you even know you're going from healthy to pre-diabetic, there are system-wide things happening in the body. Firstly, the fatty acids and the inflammation are interrupting insulin signal on blood vessels. So instead of the blood vessels being able to dilate, they become really stiff and hard, which is one reason you see high blood pressure and the starting early stages of cardiovascular disease. That same chronic inflammation is now going to the brain, and because the blood vessels are getting stiffer and blood to the brain is so important, you start to have cognitive impairment in the brain dysfunction. So you might not be as sharp, or you might have brain fog developing. That could be a result of insulin resistance, even with, you guessed it, normal blood sugar. Inflammation accelerates the aging process as well as starts to damage tissue. So if you know anything about aging, one of the things that happens is when we're young, our cells like to divide and replenish themselves. As they age, they senesce, meaning the cell just doesn't want to die, but also doesn't want to regenerate another cell, and that's when aging sets in. Inflammation seems to accelerate that process. So by having that chronic inflammation, because of the insulin resistance and the fat cells spilling over, you're aging faster. The damaged tissue and the chronically high insulin creates a growth-friendly environment and is linked with increases in cancer risk. Again, while your blood sugar is still normal. It even has implications for erectile dysfunction. As we said, it impacts your blood vessels. It makes them stiffer. And so if your blood vessels are not responding, dilating in order for an erection to form, that is what leads to ED. There's also implications for women with PCOS. So the chain looks like this. Insulin sensitive, fat cells too big, fatty acids spill over, cells of the body become insulin insensitive or resistant because the fatty acids and inflammation are interrupting insulin signal. High insulin, fatty liver, blood vessel dysfunction and inflammation, cardiovascular disease, brain dysfunction, sexual health implications, higher risk of cancer. This is all before there's a change in your blood glucose level. The tipping point into diabetes. Eventually, muscle and liver insulin resistance worsens, blood sugar starts to rise, you become pre-diabetic. The pancreas compensates by making even more insulin until it can't keep up. Beta cells burn out, insulin falls, type 2 diabetes forms. In fact, for some people with type 2 diabetes, if it gets bad enough, the beta cells are so exhausted They almost make no insulin, and you very much resemble the phenotype of a type 1 diabetic. You might be wondering, why did evolution give us this system? The thing is, for 99% of human evolution, for 100,000 to 200,000 years, 99% of that, food scarcity, not food excess, was the threat. Evolution made us extremely good at storing fat for times of famine, which were very common during our evolution. It's only been in the last maybe 50 years, arguably less if we're looking on a global scale, of when food abundance has been our status quo environment. And so evolution has had no time in order to deal with this. Okay, so how do you know if your insulin levels are too high? The thing is, most doctors don't directly check for insulin. What they'll do is they'll look at your blood sugar levels and your triglycerides and cholesterol. And if those look good, they'll say you're healthy. But as we've seen, that is not always true. A simple indirect marker of insulin resistance is taking your triglyceride number and dividing it by your HDL number. So this is a ratio that we can use. You can find these numbers on any of your standard blood work. In the US, the number should be under 2. In most other countries, because we use different units, you want a number under 0.87. Pause here, take a screenshot, and go check your last blood work. If your ratio is higher than these numbers, that might be a red flag that you are insulin resistant. The good news is insulin resistance is very reversible. Here is a list of 8 things that you can do that are ranked from the most impactful and immediate things that you can do to more long-term and supportive effects things that you can do. Number 1, it should be obvious, reduce sugar and refined carbohydrates. That means cutting out anything sugary, like sugary drinks, candies, baked goods, pasta, rice, bread, and high fructose foods. Oftentimes, just doing this shows a marked improvement in fasting insulin levels within days to weeks. 2, lose excess body fat through some form of caloric restriction. Oftentimes, just cutting out the majority of sugary foods will create the calorie deficit that you need. So not only will it help directly your insulin numbers, it will indirectly start to shrink your fat cells. When that happens, all of the cells of your body become more sensitive to insulin. As losing fat takes more time, this effect will be seen on the order of weeks to months. A good heuristic to use is 90 days. Within 90 days, if you really commit yourself to losing fat, you will see a marked improvement in your insulin sensitivity. 3, build muscle through resistance training and strength training. Why? Your muscle is the biggest sink for glucose. So the more muscle you have, the more glucose you can suck into those muscles and store before it gets shipped off to be made into fat. 4, regular physical activity in the form of resistance training, yes, but also aerobic exercise. It so happens that just by contracting your muscles, either through aerobic exercise, running, for example, or resistance training, the contraction of the muscle is a signal that can bring the GLUT4 transporter, that straw, to the surface independent of insulin. So especially if you're insulin resistant, you want to lower your glucose levels, that is one way you can get glucose to come down. Glucose comes down in your blood. Insulin doesn't need to be high anymore. It can also come down. Exercise also has been shown to decrease inflammation, again, a really strong driver of insulin resistance, and it allows you to be more metabolically flexible, because when you exercise, as opposed to glucose just being stored as glycogen, it's being burned for fuel, fatty acids are being burned for fuel, that transporter is going into the cell membrane, bringing in more glucose. It overall has all of these positive impacts on your body, reversing insulin sensitivity and giving you a bigger range of how much glucose you can take in because you are burning it as opposed to storing it. Number 5, improve your sleep quantity and quality. This is really important for reducing inflammation all over your body. Your body cleans up while you sleep. And as we saw, one of the things that happens is that the fat cell causes inflammation, cytokines. Inflammation goes up in your body. It starts to interrupt insulin signaling, and then it had that snowball effect, right? So we want to reduce inflammation in our bodies. Exercise does that. Sleep is another powerful way to do that. Reduce chronic stress for the same reason, inflammation. Stress causes inflammation in our bodies. You can do this through yoga, mindfulness, walking can be very therapeutic in nature. Find your way of doing this. Number 7, eating in an anti-inflammatory way. Yes, inflammation is a big deal when it comes to insulin resistance. So even finding ways where you can eat to reduce inflammation. Omega-3 is really, really important, especially for the brain for reducing inflammation. You can find that in fatty fish like salmon, or you can take a supplement, pill form. Another one is polyphenols. So fruit with dark skin has a lot of polyphenols, or even vegetables with dark skin, dark leafy greens. So you want to make sure you are having a lot of that, and just focusing on whole foods helps you get there. And number 8, time restricted eating. Choosing to eat in a smaller time frame. So as opposed to eating from 9 a.m. to 9 p.m., which is a 12-hour window, and then fasting for 12 hours, choosing to just eat in 8 hours, for instance, and fast for 16 hours. It gives your body more time not to have insulin in it because you're fasting for a longer time. But this is really the way that I think about it, a strategy to help you reduce your calories and or reduce your sugar intake. So a lot of people find it much easier to cut out a meal, usually breakfast, than it is to reduce their calories overall through all the different meals. So you can use this as an additive function, but really focusing on that top 6 things is going to get you most of the way there. Okay, so that is insulin and insulin resistance in a nutshell. It's not just about blood sugar. It affects your heart, your brain, your liver, and other areas. The best news is you can reverse it. Shrink over full fat cells, build muscle, exercise, and reduce inflammation. Each step improves insulin sensitivity. Understanding what is happening in your body gives you control. Start small, stay consistent, and your future self will thank you. And I thank you too for joining in. Hopefully you stuck with it. Hopefully you learned something good. If you liked this content, please go ahead and give it a like. If you want to be able to tune in to more information like this in the future, please go ahead and subscribe. And actually, the biggest favor you can do for me is if you forward this on to someone that needs to hear it, that needs this information, please go ahead and share. That would mean a lot to me. All right. Thanks, guys.